Okay, so I will be presenting my long term from the 2019 science conference that I did. I did how changes in a neural network's layering and parameters affects its accuracy. So to start off, I'm going to define a neural network, and this is just a computer system modeled after the human brain. So there are neurons in the human brain that communicate with each other, but in the neural network there are edges and nodes, and the node is acting as a neuron, while the edge is the connection or information being sent between the nodes. Now, each edge has a weight and each node has a bias, and these are just numbers assigned to them that are changed throughout the model's training to better fit the data. So feed forward is running data through the model to get a prediction, and then back propagation is changing those weights and biases, the numbers, to improve the accuracy of the model. So here's an easy example between cats and dogs if you were trying to classify them using, in this case, x1 ear length and x2 tail length. So you have some sort of input layer, and this is going to take the ear length and the tail length and connect it to an output layer, which is going to use some sort of activation function, which normally is a sigmoid function. And what this does is it just puts the value that is given in that node to a 1 or a 0, and that 1 is going to be a dog and 0 is going to be a cat. And W1 and W2 plus the B are going to be the weights and biases that you're changing through back propagation. And when you're using feed forward, you're putting different values for ear length and tail length and comparing that with a prediction that you get. So here's an example with a graph, what it would look like. So it starts off completely random. Your boundary line, which is the green line in this case, isn't really distinguishing between the red points, which are dogs, and the blue points, which are cats. And when it's finished, it's going to use all the back propagation after the feed forward to adjust those weights and biases. And the boundary line is going to somewhat fit the data, so that way it can actually compare. If you gave it a new point, it will be able to tell you if it's a dog or a cat with some degree of accuracy. Okay, so then in my model, I used a convolutional neural network, and this is just a class of deep learning, which is a subset of machine learning. And it's used a lot with image recognition because it can process a lot of pixel data very fast. And in my case, I used 3 different data sets. I did 2 that were grayscale and 1 which was colored. So the first 2, MNIST and Fashion MNIST, are grayscale, and they contain 60,000 training images and 10,000 test images. And the MNIST is handwritten digits from 0 to 9, and the Fashion MNIST is clothing items like hoodies, pants, shirts. And the CFAR10 had 10,000 less training images, and it was also colored, so it had RGB pixel values instead of grayscale. And it contained cars, planes, more everyday items that we see. So to start off with some definitions, batch size is the number of images that's going to be passed through the model at some given time. And epoch is the number of iterations through the data. So if you run the data through it 6 times, the epoch is going to be 6. And then training data, this is the data used to improve the model's weights and biases before the testing process. So I get into that more later. Overfitting, in this case, is where the algorithm is trying to train on the training data too well, and it's creating a boundary line that doesn't really fit what we normally see. So in the image all the way on the right, it's showing the boundary line is becoming too perfect. So if you gave it a new point, it's not going to be able to model that very well. So it's not going to be able to model future data. So my question was, how does the amount of training data given to a convolutional neural network affect its accuracy? And my claim was that it's going to learn logarithmically. So its rate of learning is going to be a lot larger when you're at smaller points of data, but when you become giving it larger amounts of data, it's going to slow down and it's not going to learn as quickly. So my code, I imported 3 modules, TensorFlow, NumPy, and matplotlib.pyplot. TensorFlow is just a module that's used with machine learning a lot. NumPy is used with mathematical operations, and that's what I used it for. And then the pyplot is so I can actually graph the data that I had. And I imported 3 data sets. In this case, it's the Fashion MNIST, and that's just the randomly shuffled clothing images. And then I defined labels for each of the clothing items. So in this case, t-shirt and top was 0, and then coat would be at index 4. So continuing on with this, I changed the number of training images, so I needed to set that to a different variable each time. In this case, it was 2,000, and I varied that for each experiment. And I had validation, which was held back from training, and it's used to give an estimate of what the test data is going to look like. Okay, then I had to reshape the data, so it was given as 28, 28, 1, And what this means is the first two are the size of the image, so in this case 28 by 28, and the 1 is going to be the depth. So since they're grayscale, it's 1, but for CFAR 10, those images were colored, so they were going to be 3 for RGB. And then I one-hot encoded the labels, and what this does is it takes in this case, 10 items that we had, and puts a 1 or a 0 for each of those items. And the example on the bottom left is if I had 3 items, so red, green, and blue, and instead of having a given index for an item like, say, blue is at index 2, instead of doing that, it's just going to put a 0 if it's for green and 0 for red if it's blue. And if it was red, red would have a 1 and the rest would have zeros. Okay, and then a convolutional layer, this is used a lot in the model. And what it does is it takes whatever kernel size you have. In this case, I used a kernel size of 2, so it's a 2 by 2 matrix. And it multiplies it with the pixel values, a 2 by 2, so it starts at the top left, and it takes that matrix and uses the dot product between those to get you 1 pixel value in a new image. Now it slides from left to right and continues on throughout the entire image and goes down until you end up with an image which is seen on the right here that has different pixel values. But the problem with this is that you're losing data on the outside. So if you start with that 4 by 4 image and you use a kernel size of 2, you're going to get a 3 by 3 image. So this is the main problem that we see. But to solve that, you can use padding, which is just an easy way to just say put a layer of zeros around the image. So that way after convolving, it has the same size. Okay, and then in this case, the yellow lines are commented out, so those are used later, so don't worry about those. But I added a max pooling and dropout layer, and what those do is they reduce overfitting. So max pooling is saying if you took a 4 by 4 image over here, it's going to take the max pixel value of whatever size your max pool is. So in my case, I did 2 by 2, and it took 20 from the top left, 30 from the top right, and it does this to shrink the image a little bit. And then dropout is the percentage of nodes that are not going to be activated or not sent to the next layer. And both of these techniques reduce overfitting. Okay, so then I flattened the data to have a feature map or a vector of data. Instead of the 28 by 28 by 1, it's going to have 256 nodes. So as you can see, the pooled feature map on the left is what would be happening after the max pooling. And it's going to shrink into just a vector of data. So in this case, it was a 3 by 3, so now it's going to have 9 nodes. And then I used a dense layer, which feeds all the outputs from the previous layer to all the neurons in the second layer. So if you had 256, it's going to feed all those into the next layer. And I used the softmax activation function, which takes the 10 node values and creates a probability distribution. So that way only one will have the highest probability, and that node is going to be the prediction. So in this case, if a shirt had a prediction of, say, 0.43 and the rest added up, they all add up to 1, but nothing else was bigger than that, it's going to be the shirt. Okay, so here's my model. In this case, I used Fashionum and IST, so the image is 28 by 28. I moved on to a convolutional layer with 64 filters, passed that into a max pooling layer, which put the image down to 14 by 14. And then I used dropout, so it dropped 30% of the neurons. And then continuing on, I moved it to a convolutional layer again with 32 filters instead, a max pooling, which put the images down to 7 by 7. I dropped again 30% of the neurons, and then I flattened those images. So in this case, we have 32 filtered images, and 32 filtered images that were 7 by 7. So this creates 1,568 nodes that are passed into the input layer. And this moves to a dense layer, so it takes all the connections between the first layer, which is 1,568 nodes, moves it to a dense layer of 256 nodes. That's pushed to a dropout layer, which takes 50% of those neurons and doesn't activate them. And then that finally goes to the final dense layer of 10 nodes, and these are representative of each of the different clothing items. So one of the nodes will be shirt, one of the nodes will be hoodie, and whichever node has the highest value in the probability distribution will be the prediction. So after this, I defined a loss function, and this lets the model actually learn. So in this case, I use categorical cross entropy, and this measures the performance when it's an output model between 0 and 1, which is what I had. And I had to define the optimizer, which is Atom. This is just the function that changes the weights and bias after each batch. instead of epoch, so I could have used one that changes it after the entirety of the data is run through, but I wanted to do it after each batch size, so I used atom. Okay, and then I imported model checkpoint. So what this did, it saved the model after each epoch, and it saved best only, and what that means is that if it improved from the last epoch, it's actually going to save it, but if it didn't, it won't save it. And then I fit the model with the training and validation data, and I had to define the batch size, which I always kept at 64, and I always kept the number of epochs at 1 to keep everything constant. So my first test that I did was I varied the number of training images, because this is the question that I had to start. And I was classifying between all my 3 data sets, so FashionMNIST, MNIST, and CFAR10. And I varied it from 1,000 to 55,000, and I had a step size of 1,000, so what this means, it will go every 1,000. So to start off with 1,000, 2,000, 3,000, and it'll go all the way up to 55,000. And my CFAR10, this was an issue because it was made up of RGB pixel values, so it was harder to distinguish between them. So it made the accuracy very low, and also it could only go up to 45,000 training images because it had less than the other 2. And again, I kept the batch size and epochs constant for each data set, but again, CFAR10 was very low in accuracy because of this. So here are the 3 different data sets and the accuracy of the model over the number of training images. So the blue is the MNIST, yellow is FashionMNIST, and then orange is CFAR10. And I could kind of see that there was some sort of logarithmic pattern going on, but I wanted to do more tests to see this. So yeah, my first thoughts were that it was learning logarithmically, but since I was using the same model, I couldn't really tell if that was the reason why. So my next step was I wanted to change the model and see if it learned differently when it was a new model. So I removed the second convolutional layer, I removed the second max pooling and the second dropout, and I added a hidden dense layer with 128 nodes in between the 2 other dense layers, and then I added a dropout layer of 0.5, so 50% of the neurons were dropped. And in this case, I just used FashionMNIST to see if there was any change. And I noticed that it was reaching 80% in 10,000 images when it was barely reaching that by the end for the last model. So I thought that was due to the removal of the second convolutional layer, but since I changed so many things at once, I couldn't really tell what it was from. So to start off, I just wanted to increase the number of dense layers to see if that would delay the slowing of the learning rate. So how I did this, I took the original model and I added different amounts of dense layers. In this case, I tested it with each of the data sets. So in this design, there were 3. I had a descending design, an ascending design, and then a same design. The descending, it started at 256 and continued down. The ascending started at 32 and continued up, and then the same just stayed at 256 for each one, and those are the number of nodes in each dense layer. And then I didn't count the final prediction layer because they all had that. So here's an example. If I had, say, two dense layers, and in the descending, it'll start at 256, then 1 at 28. Ascending, again, starts at 32, it goes up to 64, and the same just stays constant. And I tested this each 3 times and took the average for each point. So here's what I saw with the FashionMNIST, and I noticed decreases in accuracy with the ascending and the descending, and the same kind of stayed constant, but it was very noticeable in the ascending, so it was losing accuracy a lot. And then I tested it with the MNIST data to see if the same decrease was happening, and it did seem like it was. Ascending was decreasing much faster. Descending didn't have as strong as a decrease, but there still was a noticeable decrease. And then I tested it with CFAR10, expecting it to be the same, where ascending drops. But in this case, ascending started out lower than the other 2, and it increased after that. So it was actually almost with the same model by the end. The descending actually descended more this time. So I figured it depends on the data that you're using, and I couldn't really draw any real conclusions on this because it looked like it was different for each case. So then I wanted to change the model's filter values, and I wanted to see if that had an effect or a correlation with how fast the rate at which the network learns slows down. So I used a model with 3 convolutional layers for both data sets, and I did it with FashionMNIST and CFAR10. And the reason I did this was because MNIST was very similar to FashionMNIST, and anytime I was taking data, it didn't look like there was much difference between them. So I started with filter values of 8, and I doubled those each time. So here's what it looked like for Fashion and IST, and it looks sort of logarithmic again, where trial 1 would be the green, and I had 3 trials for each one. And as the filter value increased, it looked like it was also increasing, but it was slowing down its learning. Same thing with CFAR 10, it was increasing, but I did notice this drop off at 256. It looked like it was not fitting the logarithmic one anymore. So I wanted to see what that dip was at 256 for both data sets. It was very noticeable for CFAR 10, not as much for Fashion and IST. So I decided to go a little bit further. I went to 512 to see if that would continue to decrease after that. And I found that it increased logarithmically until an optimal number of filters was reached, and then after that the accuracy started to degrade if you further increase the number of filters. So I changed the model's number of convolutional layers next, and I wanted to see if this had an effect on the slowing of the learning rate. So I changed the original model's number, and I always kept the filter values at 64, so that way that would remain constant. And I tested the accuracies with training data between 1,000 and 10,000. In this case, it was just Fashion and IST. But the way I was doing it, it was kind of hard if I wanted to test, say, 10 convolutional layers, because I would have 10 different lines here that it's kind of hard to distinguish between them. So I did it like this, where you had the number of convolutional layers and then the accuracy for each trial here. So it sort of looked like the last problem where it was reaching an optimum number. In this case, it was 5 convolutional layers, and that was the most accurate. But it wasn't logarithmic, it looked more linear, and then it almost sloped down at the same slope as when it was increasing, which I thought was odd. And then the CFAR 10 actually reached an optimum number at 3 convolutional layers, and then after that it decreased linearly very quick. So the conclusions that I made based on my data was that the number of filters used in the convolutional layer, as those increase, the accuracy of the model also increases logarithmically, but you reach an optimum number at some point, and after that's reached, the accuracy degrades as you increase the filters further. And then as you increase the number of convolutional layers, there's a linear increase in the model's accuracy, but once you reach an optimum point with that, the accuracy starts to degrade at a similar rate or a similar slope as when it was increasing. And the final conclusion I made off my data was that the convolutional neural networks learn logarithmically. As the amount of data the network uses to train increases, the rate at which the network learns slows down. Thank you. So if I were to change anything from before, I would say I would just use more data sets, because some of the issues were that M&IST and Fashion M&IST were very similar. So it was hard to distinguish if those two data sets really had much difference. And also it's nice because in the previous problem, it was looking like everything was random and it was different for each data set, but I assume if you used more data sets, there would probably be some sort of pattern there. So thank you.